Assalamu alaikum. Welcome to Turkish Engineering. In this lecture, you are gonna find heat transfer problems from the Hoffman's book, and we start by the first chapter where we just introduce heat transfer mechanisms and the basic equations for different type of heat transfer. And at this problem, we have two types of heat transfer mechanisms, which are conduction and convection. Okay, here outside of the wall, we have an insulation layer. Okay, it's like a thin layer of 2.5 centimeters, and inside of the insulation layer you have a wall. Okay, you have a hot wall which which has a constant temperature at the inside. T wall given as 315 degrees of Celsius, and you have T environment. Okay, T infinity as 38 degrees of Celsius. You have a heat transfer coefficient here, okay, because of the convection, but you don't know. You want to find this, and actually the question wants to find that value depending on a condition given that this T out must be maintained at 41 degrees of Celsius. In order to keep this value constant, we need a balance. We need a specific heat transfer coefficient so that this temperature does not increase by time. Okay. So what happens that you have conductive heat transfer, since this is has higher temperature than the outer wall. So in the solid domain, you will have conductive heat transfer coming until this surface. Okay, and as we know, energy cannot be stored on a surface. It can be stored on a volume, but not on a surface. Okay, so here what comes what I mean that this layer sometimes comes toward the wall, and some others leaves the wall. Okay, leaves the surface. So Q in, you have Q in and Q out. Okay, and something leaves, and they must be identical to each other. They must be equal to each other because you cannot store heat at a surface. Okay, so Q in and Q out must be equal to each other. You don't have anything else like radiation or something else coming to that surface. So we will make a balance, and let's find what's Q in. Q in is just caused by conduction. So we need a thermal property for this material, solid insulation layer, which is given 1.4 watt per meter degrees of Celsius. Okay, it is given here. So we use that value, and from the Fourier's law, you know it's in a derivative form, but here we just use delta. Okay, so here delta T over delta X in order to find just heat flux coming to that surface. You have area also. Okay, you can put also area, Ka. So that means not per unit area. That will give you the heat transfer amount in watt. Okay. So we know 1.4 watt per meter degrees of Celsius. We don't know the area. Okay, let's keep it. Temperature change is just between this solid domain in inner surface temperature minus outer surface temperature as a degrees of Celsius, and you have delta X here, which is 2.5. You can say 0.025 meters. Okay. So here let's cancel the terms. Let's cancel some terms. Here you have degrees of Celsius. We'll go with degrees of Celsius, and here you have meter squared. Okay, area will be like as meter squared. So that will also cancel the meter. So you have watt. Okay, that unit will be watt. So that amount must be equal to also Q out. Q out is convective heat transfer. HA T minus T infinity minus T naught, or T naught minus T infinity, depending on which is bigger. Okay, so you take here T naught minus T infinity. Okay, I don't know H, I don't know A. T naught is 41 and T infinity is 38. Okay, so let's balance these two equations. So you will have HA times 3 is equal to 1.4 times 315 minus 41 over 0.025, and you have area here again. Okay, these areas will cancel each other. Area and area, they will cancel each other, and you can send this guy to other side, and you can find the heat transfer coefficient for this problem. Okay, so let's bring a calculator. 1.4 times okay, so we found 5,114.7, you can say. You have also here as a unit. We cancelled the value, but we still have unit meter square and here degrees of Celsius. So when you send these guys to other sites and you were having watt, so that will be watt, and the other units coming from the other side as watt per meter square degrees of Celsius, and also that can be Kelvin. Watt per meter square Kelvin or degree, because it is delta, okay? Delta T, so 1 degrees of Celsius increase means also 1 degree Celsius, 1 Kelvin increase, so that's okay. So here how we approach this kind of problems. See you at the next video. Thank you for watching.